we've had some discussion around unsupervised learning rather, when we started the machine learning bit of the course. So who can tell me what they remember that we said that supervised learning is? Anyone? Is anyone? Hello?
Yeah, supervised learning is when the
No,
data set
unsupervised.
used in, oh, sorry, unsupervised is when the data set used to build the model has been categorized in such a way that um, it's easy to actually, like, the answers have been derived, and it's easier to train the model based on the correct answers and corrections. Yes.
No. So I think you're describing supervised learning.
Are you talking of unsupervised?
Yeah, I'm talking of unsupervised learning.
Oh, that requires like very little effort on the part of the user. The bulk of the learning is done by the model itself.
Okay.
I think that falls under neural nets and rest.
No. So neural net is just an algorithm. You can still use neural nets to do unsupervised tasks and both supervised and unsupervised tasks. Yeah.
Okay.
Is there any other person who wants to speak? But what you said is close to it. Yeah, but it's correct kind of.
Yeah.
You kind of get the idea. Is there any other person? So for those of us who are going to work on customer segmentation, you most likely want to use a non-supervised learning approach for that problem, right? And one of the algorithms that you can consider is what we'll be discussing in this class today. Okay, so I'll just start with it. You can see the slide, right?
Yeah.
Okay. So unsupervised learning. And in unsupervised learning, we'll be looking at unsupervised learning itself, and then some algorithms that some unsupervised learning algorithms, that's K-means and principal component analysis. Short is PCA. And then we'll be looking at some codes, right, on how to implement this in code. So the slide is quite short, so I'll go through it as quick as possible so that we go to the code, right? So every one of us understand what we are seeing here. I don't think I can write with Zoom on browser. Is it possible to write with Zoom on browser? Oh, it's not possible. Wow. Seems like there's a big disadvantage here. Okay, but it's fine. So this is what we'll consider as a supervised learning problem where we have our training data x1, x2, that's x1, x2, x3, representing the different training examples. And then we have a y. So y is our ground truth. So it more or less gives us an idea of how far away we are from predicting the right value, right? And then we have a hypothesis function. So the hypothesis function, h, tries to approximate the value y, just like we have seen in previous classes when we treated logistic regression. I don't know if we talked, did we do SVM? I think we touched SVMs briefly, then we did linear regression. So there are so many other algorithms that there are 3 algorithms that everyone can also try out. And then this hypothesis function that approximately gives us the value of the ground truth. can then be used to make predictions of y for new data, right? But unlike, please look at this carefully and then tell me what you see is the difference between this supervised learning paradigm and what we see in this unsupervised learning paradigm. Are there any differences that you can see? What are the, or rather, what's the difference in the training data? Anyone?
There are no distinct features.
Distinct features? No. So here, so in as much as we're having x1, x2, where the numbers here represents the training examples, this x could be for different features. It could be for 10 features, and it's the same thing you can have here. So this 1, 2 represents the training examples. So, but look at the supervised learning paradigm again, and then look at the unsupervised learning paradigm. What do you see is the difference?
Sir, can you go back to
The difference in the training. Yeah. So the difference I'm looking for is the difference in the training data.
You don't have an expected output for the unsupervised learning.
Okay. Yeah, so that's right. So in unsupervised learning, that's basically the it speaks to the name of this paradigm. So supervised learning means that you're more or less supervising your algorithm, yeah, to make better predictions, and that's why you have your ground truth y. Yeah. So for every training example, you have a ground truth y that you can use to measure the loss or measure how far away your hypothesis function is in predicting the value of y. Yeah. And once your h, the loss, once your loss is very low, your h at this point will be able to make good predictions of y. So, but unlike supervised learning approach, unsupervised learning, you just have your data x. There's no ground truth y. So, but what you'll want to do in unsupervised learning is that you want to throw this data into your algorithm and tell the algorithm to find some patterns or some relationship within the data and kind of bring them together. Permit me to use the word cluster them together. So then we ask ourselves, what are we then trying to do? Or what are we trying to approximate in the hypothesis function of an unsupervised learning? And then what are we even predicting in an unsupervised learning problem? So if we go down, so there are the three elements of machine learning also applies to the unsupervised learning approach. You also define a hypothesis function. There's a loss, and then you actually optimize this loss, right? But the funny thing here is that for unsupervised learning framework, you find out that you are trying to optimize the input itself, not y, right? The loss this time around is you're finding the loss between it, kind of finding the loss between itself and itself, which I will explain better. So let me just follow. Let me not go faster than my shadow. Let me follow the slide just the way it is. Yeah. Okay, so say, but what to do? What do is a hypothesis function and loss function signifying an unsupervised learning, right? So of course, this loss function and the hypothesis function is going to be quite different from what we have in the supervised learning problems we have been working with so far. So this is the framework for a non-supervised learning problem. You still have your input features with n. You have your input rather with n features, right? And then from 1 to m training examples. Then you have your model parameters, theta, just like you have in supervised learning. But the number of model parameters will be represented with k, right? And then you have your hypothesis function, h of theta. So h of theta approximates the value of, it kind of approximates the value of your input itself. So it's what it means here is that what you would have in this question mark is x. So you're trying to approximate the input values also itself. Unlike here where we're trying to approximate the output, which is y. It might not seem clear now, but I'm sure when we take when we go into one of the algorithms, say k-means, you'd see what I mean, right? And then there's a loss function. So you're trying to reduce the distance between your hypothesis, yeah, and the input feature itself. And then of course you would want to minimize this loss. You want to minimize the loss of, minimize the value of your parameters. Yeah, you want to minimize the loss. Okay. So of course it seems odd, and I'm sure everybody would be saying that now, because what does it mean for us to approximate the value of the input? Yeah, but it's because of the way the problem is framed. And just like I said, we are going to see it in when we start talking about k-means algorithm. And then there are two different algorithms that both fit the framework of the unsupervised learning problem: k-means and then principal component analysis. So let's start k-means so that everything we've been saying kind of makes sense. Yeah. Okay, but before I start, let me know if there are questions, and then let me know whether there are things that I should answer now, or whether there are things that will be answered as the lecture goes on. Questions? Okay, so but if you are confused, raise up your hand. I hope I'll be able to see hands on this browser version of Zoom. If you're confused, raise up your hand. Okay. Okay, Sandra. Yeah. 1. Okay. So now let's look at, okay, what's confusing you, Sandra, before I move on? You can speak up. What's getting you confused? Sandra. Okay. I'll just move on. Okay, so let's look at k-means. Okay, so but before I start k-means, does anybody know anything about, has anybody tried doing anything with k-means algorithm before now, or has anybody heard of k-means and has an idea of k-means algorithm? If you do, you can just tell us what you know about k-means algorithm. K-means algorithm, yeah. Anyone? Okay, no one. Okay, so but I'll ask another question. Has anybody, does anybody have an idea of what segmentation is? So the popular one, customer segmentation. Has anybody done anything around it, or have you heard things around it, or have you read stuff about around customer segmentation? If you've done something like that, just tell us what you think it is. Okay, nobody again. At this point, I think maybe you guys are not hearing me, or maybe my network is bad. Can you guys hear me?
Yeah.
Okay. Okay,
Yeah.
so but from the top of your head, anyone, what do you think customer segmentation is? Anybody can speak. Just raise your hand and then speak. You must not be perfect. We are all learning, guys. We are all learning. Okay, Fatima. Fatima, you can speak.
Okay, so in my own little understanding, customer segmentation is looking at the base of your customers, looking at their spending patterns, and being able to identify the ones that are probably be high spenders, medium spenders, and low spenders, put them in buckets to say that these customers behave similarly, from my own understanding.
Okay, that's nice. That's nice. So, but Fatima, if you are going to implement, a customer segmentation, say an application or a script or something, how do you think you would go about it?
Okay, so number one, I will look at their for example, their spending patterns.
Okay.
To say that this how much does the person, what's the minimum and maximum amount this person spends per month, or on the average get the spending per month for all the customers, and then use that to say that this is high spender, medium spender, and so on, or look at a couple of other patterns in their spending to be able to arrive at the conclusion that this person seems to be a medium customer, this person seems to be a high-end customer, this person seems to be a low-end customer. So basically, I will look at their spending patterns.
Okay. Can I ask one more question? Sorry, please.
Okay, go on.
Okay. So now, how long do you think it will take you to write a code that would, or to come up with a flow that kind of segments customers? So how long do you think it will take you to identify these patterns? Of course, you're going to have distinct features that you're looking for. How long do you think it will take you to then put up probably a flow to segment this customer?
By flow, you mean their data collection, that is maybe collect their data for a period of maybe 3 to 6 months or 1 year?
No. Now let's assume you have the data. Yeah. How long do you? Let's say now you have, say, let's assume it's a bank data, and then the bank has say 500,000 customers, and these 500,000 customers, they've been able to collect about 50 features from these customers. How long do you think it will take you to segment these customers?
How long?
Yeah.
Okay, so assuming that I'm an intermediate data analyst, within 2-3 weeks I should be done, including writing the algorithm that will make the predictions.
Okay, nice. Okay, so let me not go further. I would like to ask more questions.
No,
so
please do. Please do, Kenneth.
Okay, let me ask one more. So what do you think, on a scale of 1 to 100, how accurate do you think your algorithm would be?
If I'm able to get to anything above 80% accuracy, I'll be fine.
80. Okay. So let's just move forward. So before I move forward, Sandra, I just noticed that because I've forgotten the chat. Remember, I'm using the browser version, so I don't usually see notifications. So Sandra is saying, can the ground truth also mean test data? That is, to test how good our training data performed in the algorithm. So no, ground truth does not mean test data. Ground truth is the true values. Let me use the word true values. Okay, so now I'll give you an example. Remember when we discussed about house prediction, and then you say we want to predict houses, right? And then you have different features of the house. You have the size of the house, the location of the house, the number of rooms, you get, and so many other features. Those are your X features, right? Now, the price of the house that is in that data set, that's your ground truth, that's the Y. So what we're trying to do is to come up with a hypothesis H of X that will approximately give us something close to the value of Y, which is the ground truth. Yeah. Okay, so but I might not be able to go through it very well now, but if you need more clarifications, we can still discuss it maybe on Slack or anywhere. Yeah. Okay, so let's move on. So now let's now talk about K-means algorithm. And as we are going to start K-means algorithm, you guys should have in your mind all the discussions I had with Fatima. Yeah. Okay. So this is what K-means algorithm is. The K-means algorithm is easy to visualize, yeah? Given some collection of data points, we want to find K centers such that all points are close to at least one center, yeah? So this is what it looks like. So you have a data that is plotted on, say, a 2D plane, and you want to find centers that are close to, you want to find centers such that all points are close to at least one center. So you find out that for this particular point, the data points marked with red are all close to this center mu of 1. That's this red circle here. And all these points here that are colored green are all close to this center mu 2, marked by this green circle here, right? And okay, so there's no much explanation here. So let me just do the explanation on my own. Unfortunately, I can't write because of this my limitations here. So now this is what it is. The K-means algorithm kind of tries to cluster the pictures in your data sets based on similarities, based on patterns it finds in themselves, right? So now I was discussing with Fatima, and she said she would find the patterns and then probably write an algorithm, and it might take her 3 weeks. But if you're going to be using a K-means algorithm, this is what it is. You have a data set, right? Let's say it's a data set that you can plot in a 2D plane, and this data set is scattered, right? In this, just the same way, just the way you're seeing it on this diagram that we are seeing on the screen, right? Now, assume that there are no colors and then there's no red point. So what you want to do is that you want to use K-means algorithm to define centers K or centers mu, yeah? And then you want to you want the algorithm to on its own find points that are close to these centers. So now the points are close to these centers based on how similar they are. You understand? Now, in the sense that, yeah, all this, okay, I don't know, how do I put it now? I think I need to write. Okay, let me think of how to do this best. Please give me a second. There's nothing speaking to it here. How do I do this? Okay, now we have 2 data here. Yeah, we have just 1 data here, rather, and they're plotted on this time around. It is not X and Y, it's X and X, right? So it's probably X1 and X2, right? Just imagine picture this imaginary line here, right? And an imaginary line here. And then say this is axis X1 and this is axis X2. And then you have this data plotted on this 2D plane. Now, from the top of your head, if I told you pick 2 clusters from this data I have plotted, right? From the top of your head, what you would do is just to settle that, oh, these guys are kind of similar because they kind of cluster around together, yeah? And you would say these guys are kind of similar because they kind of cluster together. But now you want to do this with an algorithm. You want to do this in a more complex way, because what if you are caught in a situation where you have a data that has 3 features? It means it's going to be 3-dimensional. If you have 10 features, it's going to be 10-dimensional, and that's quite complex to visualize and complex to cluster, right? So, but from what we want to do now is use the k-means algorithm to find clusters and then look for points that are all close to these clusters. So for the points that are close to this, that are all close to these centers rather. So for the points that are all close to this center, it forms a cluster, right? And for the points that are all close to this particular center, it also forms another cluster. So these clusters can be seen as the different segments of this particular data. I think I explained it better this time around. Does it make any sense? Does it make any sense? If it doesn't make any sense, I can go over it again. Makes sense now, yeah?
Yeah.
Okay. So really, pardon me honestly. I thought I was going to use Zoom. I had it in mind to write while teaching, but it's well. So, but how do we go about creating this, choosing these centers? How do we go about creating our clusters for a given data set? Yeah. And this is what it is like. You would want to define your parameters, and your parameters are these centers, mu. So you can define the number of centers that you want to define, that you want for your this particular problem you want to solve. Mind you, if you pick 3 centers for this particular data, it means it's going to form 3 clusters. If you pick 4 centers, it's going to form 4 clusters. So it's going to find similarities even in this cluster that you are seeing here. It will still separate it. So it might say, okay, this is one cluster, or maybe say this is one cluster and this is another cluster. And you can come here and say this is another cluster and this is another cluster, because it has found some similarities and some patterns that are not in this particular cluster here, right? So, like I said, your parameters is going to be this mu, right? And then you would want to find the points, mu, you want to find the points that are closer to these clusters in this data. So let's say, yeah, we already know this point is here. So you're trying to find the points that are closer to this center here. Of course, if you compare the distance from this particular green X here to this red point, and the distance of this green X to this point, you would agree with me that it's closer to this mu2 than to mu1. That is why it's forming a cluster with mu2, right? So that's what we do here. We find the center closest to the point X, right? So that's why you use argmin, which is the minimum distance, right? And then you define your loss function to know how far it is, or how far your hypothesis is from the real value, and then you do an optimization. So the truth is that if you look at it this way, if you look at the k-means algorithm critically, it's actually a non-convex problem, meaning that unlike supervised learning problems that we were working with, where you would have remember this curve? There's a curve that was like a U-shaped curve, and then we were trying to optimize it. That was kind of a convex. That's a convex problem where we are trying to get to the minimum point of the loss. But k-means algorithm is not as such, because it doesn't have a closed form of solution. There is no let me use the word, there's no point that you're trying to get towards, right? There's no minimum point if you consider that curve U, right? And instead of having this optimization where you're minimizing the loss that you have defined here, what you will do in k-means algorithm, or what is being done in k-means algorithm, is what we have here. So this is what the k-means algorithm is itself, right? So the first things you do in the k-means algorithm is to first assign points nearest to nearest clusters, right? And Then you compute the cluster centers as mean of all points assigned to it. So what you would want to do is you have a data set, you would initialize random values of your centers, mu, right? For the different number of clusters that you have defined. So here we said we want 2 clusters, and then we defined mu1 and mu2. So mu1 and mu2 are the centers, are 2 centers because we have 2 clusters, right? And we'll then find the distance between our mu and the data, our input data x, right? Find the minimum distance between our mu and the input data x. So it is for all values of mu, and then we pick the one that has the minimum. We pick the x value that has the minimum distance to mu. You remember? So now, if we say we have 3 mu values, or in this case 2 mu values, we compute the distance between this x and this mu. And then we also compute the distance between this same x and this mu, right? And then we pick the one that has the minimum distance. And of course, this is the one that has the minimum distance. So we assign it to this particular cluster, right? And then we move on to then calculate the mean. So the mean is more or less like calculating it's more or less like you are moving these values of the mean. So based on how close, because you are not moving this value, the x value, you're not moving your data points, you're moving your mu. So now based on which one is close to your center mu, you then move your mu, right? You move your mu by calculating the mean of your mu over all the data that was pointed towards it, right? And then when you move your mu, you then recompute the distances again, and then you go on and on and on, right? So we are going to look at it in code. I think it will be clearer in code. But before I move to code, does anybody understand anything I said here? If you don't understand, I will explain it before we move to the code, so it makes more sense. Oh, someone is tired. I think it's Jamie that's tired.
Yeah, can you go over it again, please?
Okay. Okay, so let me use this let me go use this diagram to explain it. So imagine that so before I use this data, let me be sure that the writing material is not here, because I honestly want to write. Okay, so it's not here. It's fine. No problem. Okay, so now imagine that this is all data that you plotted on x1 and x2 axis. And then there's no red points, there's no circle mu and mu here. So the first thing you would want to do is to define the number of clusters that you want to create from this data, right? So let's, in this example, we say 2 clusters. And this cluster is what is going to inform us of the number of centers we want to define. And the center is mu, right? So yeah, we say we want 2 clusters and we want mu. But how do we find similarities between the data set, or how do we find patterns in this data set, given that we want 2 clusters and we have 2 values of mu? So now this mu is chosen randomly, right? And it's chosen randomly based on the minimum and maximum value of the data that we have, right? So it invariably means that it is going to be a point on this data. So let's assume that our mu1 is somewhere here and our mu2 is somewhere here, right? Now this is where this 2 mu starts from, right? Now, the next thing you want to do is, okay, now these data are static, right? We need to move these mu, values of mu, and then we need to find a way to move these values of mu and kind of find the distances between this data and the value of mu, right? Such that if we can, the ones that have the minimum distance between themselves and mu would form a cluster. So now let's say mu1 starts here, right? What you would want to do is to find the distance between mu and every of these data sets. So you're not saying you are doing mu and just this data set. Already, you don't even know if this is a cluster yet. You just know you want two clusters, right? So your mu is here. And then you check the distance between mu and some data here, and mu and some data here, right? So now, when you calculate the distance, right, and you pick all the minimum distance, right, you might find out that, okay, the distance, the data that are closer to mu will be maybe some data here, right, say 1, 2, 3. Let me pick 1, 2, 3, and then all the data here, maybe excluding this particular one. And this is the data that forms the first cluster for mu1. And then this guy here also says that, okay, this is the data that forms the second cluster. This is your first iteration, right? Now it goes again. No, now this is your first iteration. This is the cluster, right? So now your mu started off at this point. So for you to find the new center, your new center has to be a center that represents this data set that it has collected, this one here, right? So you might find out that from here, your mean might move to somewhere here or here. So how you calculate your mean is just how the normal way you calculate your mean, which we'll see in the code. So but the idea is that it says, okay, the new center I'm looking at from this new cluster I have created is somewhere here. And this one is saying, oh, the new center I'm seeing now is maybe somewhere here, right? Now it goes again. It picks all the data, calculates all the distance between itself and the data, and then says, okay, I'm seeing that these guys that I neglected here before are actually closer to me compared to these guys here. So it means these guys are going to form a cluster. Why don't I pick these guys as a cluster? And this one that is somewhere here is saying, comparing this guy and this guy to myself, I think this guy is closer to me, right? So why don't I form a cluster with this data set here? So it forms a cluster with this data set, forms a cluster, and then we calculate a new center for mu. And when you calculate a new center for mu, it says, okay, I'm calculating the center between all these data sets. It might be somewhere here. Okay, so it moves itself to this point, and then this guy also moves itself to this point, and that's how you see that. And so it might not be as easy as this, where we have just two iterations. You might go, you might have maybe 100 iterations or 50 iterations, depending on the kind of data you have, until your algorithm is able to find good centers in the data set. So now for this particular problem, we now say that, okay, this guy forms a good cluster and this guy forms a good cluster. And if you keep running the algorithm, you will find out that your value of mu might not shift from this position, because this is actually the mean of this particular cluster, and this is actually the mean of this particular cluster. Does it make sense now?
Yeah, it does. Thanks.
Okay. Is there any other question? Does anyone have any other question? Does anyone have any other question, any confusion, especially those who are going to do customer segmentation? In as much as there are libraries that you can just throw in your data to, and then you get your result. It will be very nice if you understand how it works, right? Understand what your K is, understand what your cluster is, your centroid, and the rest. Yeah. Okay, so let's move on. So what I just explained now is what we have here. It's the same exact thing we have here, right? So we are going to say we have a data X with M training examples. We define our cluster, and this our cluster informs us of what the number of centers we are going to have, right? And then we compute the cluster, right? Like I told you guys, we check the distance and then pick the minimum distance. And after we have picked the minimum distance, we update the values of mu. So remember I told you mu is our parameter. We want to continually update the value of mu until it's not changing anymore. So in updating the value of mu, we are just calculating the mean. yeah, for the different clusters, from 1 to k. And if you're going to write this in code, you can actually write it in this. It's quite short, so you can use what? I think this is SciPy, I think, or scikit-learn. I think this is scikit-learn. So you can just run it with this short code here. But there's a code that we are going to use which implements this algorithm here, so that you see how it actually works. Yeah, for each line of the pseudocode that you're seeing here. And this is what it is. You have this data scattered on this plot. This time around, it's 3 clusters, not 2 clusters. So they're all scattered, and then it starts out as with 3 clusters, and you can see these 3 clusters are just kind of randomly picked. And you'll notice that this particular one I'm hovering around is trying to classify everything here as red. And from the top of your head, if you look at it, this is a cluster, and this is a cluster, and this is another cluster. So, but instead, you're seeing that this one here is picking some data points here and saying this is green, and this one is picking some data points out of here and saying it's red, right? So, but if you keep training, you find out that it kind of adjusts itself to find better, to find through the mean, it kind of optimizes itself and then finds a better cluster. And as you go on, you see it's more of what you want now. So these are the 3 clusters. And okay. And so what, of course, in as much as we have this working fine, there's a very high possibility that your k-means algorithm might not perform well, and then it might have something like this as its cluster, right? So if you have something like this as its cluster, it might give issues, right? It might tell you, hey, I found the perfect cluster, there's no loss again. But truth is that it hasn't actually found a good cluster. So sometimes what you might need to do is train it for a longer time. That's one. And in this case, I feel the problem is that it wasn't trained for sufficient number of times, and meaning that you need to also have a way of calculating the loss, which we'll see as we go on. Then another thing is that yeah, it might be stuck at a particular cluster it has defined. So what some machine learning engineers do is try out different random initialization of the value of mu. So remember that in the algorithm above, yeah, we said we are picking mu randomly. So what some machine learning engineers do is, okay, in as much as they've gotten a cluster with a particular algorithm, a particular random initialization of mu, they try out another random initialization of mu, and then create different versions of the solution, and then pick the one that has the least loss, right? Okay. This is another example of a bad k-means algorithm. So now this one is training and finds out that, okay, it thinks this is a cluster, right? And this is another cluster, and this is another cluster. For this particular one now, it's stuck. So if you try out another random initialization of it might give you a different it will most likely give you a different result as compared to what you have now. Yeah, so it's still the same thing. So, but apart from what I have said, there's another way of calculating there's another way of addressing poor clusters, and that leads us to what we call the k-means plus plus. I've actually not really tried k-means plus plus, but it's something that it's worth trying though. So, but with k-means plus plus, what you'd want to do is sequentially sample, just as is written on the slide. You don't want to pick mu randomly from all clusters, or for all clusters rather. You want to pick mu sequentially and in such a way that it's sampled with probability proportion proportional to the minimum square distance of all the other centroids, right? So what we mean is this. Let me go down to the algorithm. So it's more or less like you want to, first of all, have a probability of the different centers or where the different centers should be before you even start out your algorithm. So it's not unlike what I described earlier. Yeah, you are still picking the values randomly, but this time around we are restricting it to a probability, right? So this is how it works. You first start off by picking the first mu, right? Just like it is in this algorithm. You start off by picking the first mu, right? Randomly for the data. Let's say this is the first mu. You pick the first mu. This is it here. And then for you to pick the next mu, you kind of find the distance between the mu, like it's more or less like finding the distance between the mu that you have found initially and the new mu you want to find as a probability. So you don't want to just pick all the mu's, but you want to pick a mu such that it is dependent on the position of the first mu you have selected earlier, right? And okay, so how do you select K? So it says there's no right way to select K, that's the number of clusters. Larger K virtually always will have lower loss than smaller K, even in hold out set. So hold out set means your validation set, right? And the truth is that the number of clusters is actually dependent on the machine learning engineer or the whoever is doing the work. So for this example that we looked at above, let me take you guys back. From the top of your head, what you would want to say is, what you want to define is two clusters. This cluster and this cluster, right? So, but depending on the kind of work you're doing, you might say, no, I actually want 4 clusters. And you can say 4 clusters, this and this, right? That particular approach is dependent on what the researcher is doing or what the researcher wants to find, right? Then you can also look at the clusters as a function of the loss. So now, if the loss, as you would see down here, where is it? So now this is the loss. I'll show you guys how to plot this on when we move to the code. I hope we still have time. Yeah, we still have some time. So if the loss is low, then you can say, okay, I have a good number of clusters. But if the loss is high, you'd say no, you don't want that number of clusters. You want to increase the clusters, and the loss is a function of the distance between the centers mu and the data, right? So now, if I say I want 2 clusters in this data, you might find out that one of the clusters is somewhere here, and one of the clusters is somewhere here, right? Say just here and here. And from here, you can find out that the distance between this center and some of the data points is very, very large. So that kind of gives you a sense of, okay, this is the loss. This is how far it is from the center. And you can say, okay, since it is that far, let me increase the number of clusters and see if we can find more patterns in this data. And then it goes on and on until you find a very good value of the loss, right? So like I said, it's dependent on the researcher, and then if you want to go through the defined loss that through a defined loss, then it's fine. Or through the loss function you're getting, rather, it's fine. And he implemented this, the professor implemented this on real data, MNIST data. MNIST data is a data set of handwritten digits. I really thought we were going to go through the MNIST digit classification, but what I'll do is to send, I'll probably send a notebook where it's implemented. It's still the approach to solving the handwritten digit classification is It's just like what we did in, similar to what we did in logistic regression last week. So you can just go through it and then just try it out, right? So now, so now with the MNIST digit classification, you can kind of cluster. In this time around, you're not clustering the digits, kind of. You're clustering pixel values, right? So if you cluster the pixel values, you find out that what you would have is something similar to this. So it's kind of clustering colors together. So you see it's a bit faint, right? And we'll see an example of something similar to this in the exercise, right? Unfortunately, I noticed that the video for this class was actually pulled down. I don't know why, though, but it's fine. We'll just move on, right? So, but unlike we are going to look at the principal component analysis, and the principal component analysis is quite different from the K-means algorithm. I honestly wish I was able to write, because principal component analysis kind of requires me to write. But let's see how we will be able to do without that functionality. Okay, so now, but look at principal component analysis as a way of simplifying data. So let's assume you have let's assume you have let's say a 10 feature data set. Sometimes your data sets could have more than 10 features, right? Could have, say, even 100 features. But now let's say we have a data that has 10 features. How would you visualize such data? Can anybody answer? Anybody in the class? Okay, but before we even talk about that, is there any question from K-means algorithm? Any question? Okay, it's recording. Any question?
Yes, sir. I have a question. If
Okay.
after running your algorithm and
Yeah.
it gets the wrong clusters, how
Yeah.
do you know it has the wrong clusters? Like in the slides you showed us, the data points were color coded.
Yeah.
So is that going to be as a result of the algorithm too? Will the data points be color coded normally, or is this something different that has to be done?
Okay, so now the reason why you're having it color coded, if you look at it from the codes, is that you kind of, each cluster that you define, you kind of pick the different data points and kind of put it in something like a list. I don't know if you get what I'm trying to say. You kind of tag them like, okay, this belongs to this cluster. And then when you are plotting, you just say, okay, for this particular cluster that you have defined or you have saved in probably a list, color code it as red, right? So now, for wrong clusters, the truth is that, would you really say it's a wrong cluster, right? You wouldn't really say it's a wrong cluster, because there's no ground truth to justify your claims that it's a wrong cluster. Mind you, it's an unsupervised learning problem. It's finding patterns on its own, right? It's finding the patterns on its own, and it's saying there is a pattern between all this data, that there's a similar pattern with all this data I have seen, right? And remember I said the only way you can know, okay, whether it's a good cluster, not a correct cluster this time around, is this loss that we defined here. And this loss kind of tells us the distance between every point and a particular cluster, right? So you won't really say it's a wrong cluster. It found a pattern, right? And then I told you also, if you randomly initialize the value, the mu, you'll always, if it's a good cluster, you'll find out that compared to other, now that is if the number of clusters that you've defined is constant, right? If it's a good cluster, you find out that the loss, right, is going to be lesser than every other one that you have tried out before, right? So the loss means that it found more similarities between this new cluster that it has seen compared to other ones. Does it make sense, Wally? Or should I go over it again?
So yeah, the explanation makes sense. I get
Okay.
it now. Yeah, thank you.
Okay. Okay, is there any other question?
Hello, can I?
Yep.
Yeah, sorry, mine is not a question, but because of the next section we are going to, you might want to consider using probably a free online whiteboard. Probably you can just write on it to explain it.
Oh, okay. Okay, that makes sense. Please, recommend one for me. Okay, let me put free beside it so that it will be free. Okay, makes sense. Seriously, I wish I knew there was something like this earlier. Let me quickly get my meeting. Okay. So while it's coming on, I asked a question earlier. I was like, how would you visualize a 10 feature data? So meaning that it has 10 dimensions. It's not more real life. It's, real world is 3D. This time around it's 10 dimensions. I don't even know if space is up to 10 dimensions. The battery is low. Wow, I can't use it. So how would we visualize such data? Anyone? Okay, let me go to the one we know. Sorry. Let's say this. So now let's say this is wonderful. Sorry. I like when my things are nice, but I think I'll just go x1, x2, and x2, x3, right? Okay. So if we have some data here, right? Say some data here, are all here. Somewhere here. Sorry, pardon my drawing. I'm using my mouse and it's not so convenient. Like I'm not used to it at all. Yeah. Okay, so if we have some data here, right? It's 3D now, it's not 10D like the one I said earlier. Now I've been able to visualize it. Does it make any sense? Let me check if there's any chat because I have to go back to see if there's a chat. Does it make any sense? Anyone? Please just use the mic because I won't be able to be going back to see if there's a chat. Sorry.
You mean the okay, yeah,
This 3D one. This 3D one I drew here.
Yeah.
Does it make any sense?
Yes.
Huh?
It does, I guess.
It does.
Yeah.
Okay. So I would ask, is it, let me put one more point here. Are the data positively correlated or negatively correlated? And then from this thing you're saying here, can you form a cluster? Just, no, I'm not talking about k-means algorithm, but can you draw a cluster from this 3D diagram?
Yeah, I guess each section, like each of the three sections would signify any points contained in each of the three sections can be a cluster. Like, for example, the section between x1 and x3 can be a cluster. Then the one between x1 and x2 can be a cluster too. And as well as the one between.
So you see, the thing is, it points on a 3D plane. So it's a three-dimensional thing. You have x1. So this point here has x1, x2, and x3, right? So what you'll be having is something maybe 1.1 point something, and then another value, something, another value, say 3. So I'm so sorry that I can't write, I don't know how to write on this thing. Sorry. Let me see if I can do something better. Say 1.2, and then this is a bracket, and then say 1.4, and then 0.3. Yeah. So now this point represents x1, x2, x3. So these points define this position here. Right? Okay, so let's move on. So the truth is this, yeah. In as much as it's good sometimes to plot 3D, have 3D plots and see some nice things and all that, most times your 3D plots don't actually give us a good visualization of what the data is. Sometimes, right? And if you're going to be doing, say, a presentation to some management team and all that, and you give them a 3D plot. With 3D plots, you can't really just look at it and then understand what the data is all about. You won't. Do you get? You won't actually understand it because it's three-dimensional. There are some things that how do you know whether this is towards the forefront or towards the back? You won't, right? So that problem is kind of what principal component analysis is trying to do, in as much as it's not really limited to that particular problem, but we'll see other problems. So, but this is what principal component analysis is. Sorry, let me clean up this. Okay, I think it's on the slide. Don't worry, I'll just go to the slide. So let's say we have my battery is going down. Wow. Let's say we have some data on a 2D plane. Now let's assume it's a 2D plane. It's a 2D two-dimensional data, right? X1 and X2, and it's plotted this way. Now the idea of principal component analysis is this: you want to find a plane, or you want to find a projection, right? Say this dotted line here, such that it is more or less represents, it's more or less compared to every other line that you can actually draw, it gives the minimum distance between the point and that particular projection, right? So what it is this: you have a 2D plane, you want to reduce it to a 1D plane, right? This is a very simple example. You have a 2D plane, you want to reduce it to a 1D plane. It invariably means that you want to find a projection, right? This projection here, which is your principal component, and then you want to position it such that every point on the data set on this 2-bit plane has its minimum distance between itself and that plane itself. So now that is perpendicularly rather, not this way. If you're looking at it this way, you'll be talking about linear regression, but you look at it this way, perpendicularly. So if you check the distance between this point and this point, 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 all together, and you check the loss, it must be less than every other line that you're going to draw. And then what you do is you move this particular point to this point on this plane, right? And then this plane gives you a new dimension, or your new dimension. So now this is 1D instead of 2D. So this is what principal component analysis does. So now, apart from the fact that it's used for visualization, right? You can also use it for compression. Let's say you want to compress large data and you want to just compress things together, right? You can just pick features that are close to a particular plane. Let's say you have a 10D data, right? A 10D feature, a 10-dimensional kind of data, meaning you have 10 features, and you want to reduce it to 5, right? So it picks values that are close to your component, your principal components, right? And let's say it's your principal, your data is 10D, and you have your principal component in say we already said 5D here. So it will bring everything that are close to that projection that you have defined, and then forms a new form of data out of that dimension you define, just like we can see here, right? So we have this, and then every other point that is closer to this point forms this particular 1D plane that you're seeing here, right? Okay, before I move, is there any question?
Yeah, there is.
Okay. I can hear you.
You said the PC is used to compress data sets to reduce the features. Is it only restricted? Is it only restricted to unsupervised learning data sets? Unsupervised problem rather.
So it's you can actually, even though I haven't tried it though, but you can still use it for supervised learning problems. Let's say you have your y and your x, and you know that the values of your of your x, right, is let's say for a particular data point, the values of your x gives you the value of y. You can still compress or simplify that data. Instead of having the 10 different features, you can simplify it to maybe 5 different features, right? It's still going to give you the output y. Hello?
Yeah, I can hear you.
Yeah, so it's but the idea of principal component analysis, it's unsupervised way of reducing reducing the data. Do you understand? So now remember, when you are using principal component analysis, you are not considering the value of y. What you're concerned with is your x. So it doesn't even know what your y is. All it just knows is that I'm giving some data, which is your features, which will always be your features. And then I want to find patterns in this data and reduce it to a different dimension, or change it to a different dimension, transform it to a different dimension.
Okay.
Okay. Okay. So so the PCA problem is defined this way. It has that, we might not need to go through all this though, but because the computation is quite complex, I must say. So first things first, you should have a normalized data for the PCA before you do the PCA problem, and that's the same for your K-means algorithm. Your data should be normalized, and then you have the hypothesis function U. So the value of U is, let me be sure so I don't make a mistake. I'm not too familiar with the mathematics. Yeah, singular value decomposition. So it uses a singular value decomposition method. And I can remember clearly that I was supposed to do something around singular value decomposition back then in school, and it's not an interesting mathematics. It's interesting though if you lay your hand on it and then you find reason to do it, but I didn't find reason to use singular decomposition. I think I used something around Galeckin's method then in school. So, but it uses the singular value decomposition method, and just like every other machine learning problem, you have a hypothesis function. This is your hypothesis function, taking into consideration these singular value decomposition parameters. So your parameter is this u, which is related to singular value decomposition. Then you have a loss, right? So still your loss is the square distance, like in k-means, and then you want to optimize. And for PCA, yeah, so this is what we want to do. So for PCA, yeah, we can reduce these values to this 1D dimension. And because you're using a singular value decomposition method, yeah, you can actually transform it back to the 2D shape. So the 2D shape that you're transforming it back to is not going to be this exact thing you have here. It's going to be an approximation of what this is, right? So it's going to just project it back to that same plane that you have. Already it has saved some, you would have already saved some information of what this plane is like, given this data here. So it's basically this, in as much as we have these formulas here. Let me see if I can explain it for you guys. So what you have is your H is your U W of X, right? Your UW of X. Now, if you want to get your X back, this is usually your UW transpose. Let's take this as, say, theta of phi. You say your phi transpose of X. So now if you want to get your X back, right, it's going to be your H, which is your hypothesis, times your UW, right, to give you this back. All right, I hope this is right. So to give you this back. I don't know why this is written here, but that's what it is. So to get this particular shape, it's this transpose of X. Okay, yeah, sorry. It's this transpose of X, right? But to get back the value of X as it is here, you're just going to be multiplying this W by your H here. I think this is mathematics. Well, you don't need to bother yourself about the mathematics, right? And then PCA is also a non-convex problem, right? Just like in K-means, you don't have that U shape that you want to go down, minimize the values of theta such that the loss is no. So you just like in K-means, your loss is basically a function of how far away it is from that projection you have defined, rather. And this is the algorithm using singular value decomposition. So for those of us who have, yeah, this is what I was looking for. Okay, so it's written here, singular value decomposition. Oh. So for those of us who have time and want to go through singular value decomposition, you can go through it and then see how it is applied to PCA. But mind you, you have to understand singular value decomposition first before you apply it here. But since you understand the whole idea of principal component analysis, you can go ahead and then use some algorithms that have been defined on scikit-learn and other libraries. And then this is a code to implement PCA, right? So you can also run this code at your spare time. But we implemented it in the code that I'm going to show you. Okay. Sorry, I think my system is hanging. Okay. So for dimensionality reduction, okay. So now, for the MNIST data, we all know that the MNIST data contains 10 digits, right? 1, 2, 3, 4, 5, 6. And you can see here that it has reduced the 10 digits to a 2D plane, right? So 10 digits means 10 features, right? Or rather 10 classes, but kind of reduced each of the features in that 10 digits to what we have here. So here we kind of see the projection of all the features, which are the pixel values in the 10 digits on this 2D plane here, right? And then I didn't go through the video. Like I said, I didn't watch the video, so I don't really know what he was trying to do here. But from here, you'll see that this is what the original MNIST data looks like, right? And then remember I told you you can use it to compress data, compress the values of data. Now let's say we have k equals 2. You find out that it kind of compresses the information that we are giving here, that we have here. K equals 10, it compresses it further. And k equals 100. So what this means is that the more, the larger the values of k, meaning the larger the values of dimensions you want to define, the more it kind of gives you a better visualization of what the data is when you uncompress it. So now this images you're seeing here is not in the you're not seeing it in you're not looking at it in the compressed form. So they uncompressed it after compressing it with a k value equals 2, and this is what you have. Of course, it has lost so many information. That's why it looks this way. And then when you have a larger dimension, of course, you can still see some of the information here. Right. We don't need to go through this. So that's it for PCA. Is there any question before we move to code? I think I have just about 30 minutes. I need to plug my system so that it doesn't go off. Is there any question? Is there any question, please? Questions.
Hello, Kenneth.
Yeah? Okay.
Yeah. So I didn't really get the PCA stuff regards the INNIST database. How I didn't get that part clearly.
Okay. Okay. Just give me 1 second. Let me quickly plug my system before it goes off. I think my UPS should still be fine. Give me 1 second. Okay. So I'm saying, remember here. Sorry for the noise. I told you guys that we can compress this data given here, this data we have here. We can compress this data that we have here, which is 2D to 1D, right? And then if we have it as 1D, doesn't mean that we are stuck at 1D. We can revert it back and have an approximation of what we have here, but it will be this, right? So now for the MNIST data, this is what we have. This is what the MNIST data looks like, right? Now, if we compress it and say we want to compress it to a 2D shape, and then we uncompress it, this is what we are going to have. So you would notice that we've lost a lot of information from this compression that we did, right? And let's say you want to compress it to k equals 10. That doesn't mean that you might not find some similarities when you plot it. It depends on the kind of data set, right? Now let's say you define your k equals 10, right? So meaning you want it to be 10D, and you uncompress it. This is what you're going to have, right? And then notice what happens when you change it to 100, meaning 100 dimensions, you can see that you can still see, you'll be able to at least know that, yeah, this is a 5, this is a 3, this is a 4, this is a 3, this is a 1, just like you have here, a 5, a 3, a 4, a 3, a 1, right? So who knows, maybe if you increase it to say maybe 150, depending on the kind of data set, again, like I said, it might even be maybe something clearer than this. So, but this is just more or less like a compressed form of what you have here, right? Makes sense? Dina,
Yeah.
does it make sense?
Yes, it makes sense. Yeah, but what's K actually? Maybe I didn't get what K means.
So K is, if when we did K means algorithm, K was the number of clusters you want to define. For PCA, look at K as the dimensions or the number of components you want to define, right? So now look at it as, take it as the dimensions you want to you want to reduce the data to, right?
Okay, okay.
So now let's say here your K it's 1, you just want it to be 1D, and then it reduces to this, right? And then you're taking it back, is going to be this. Does it make sense?
Yes, it does now. Thank you.
Okay. Any other question? Let me try and see. I hope my notebook is still running. Let me stop, 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 stop. Let me quickly start my okay, so we are going to the interesting part. Of course, me, I like the interesting part. Yeah, seriously. What is it? Okay. Okay. So in this notebook, we are going to be looking at K-means algorithm and principal component analysis. So let's just look at it closely. It's very, 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 trust me, everyone would want to try it out when they get home. I actually have an assignment right after a practice assignment after this. So now, for the K-means algorithm, we are using some data, right? And this data is of shape, it's 300 by 2. So I don't really know what the data set represents. It could be random data, and there are 300 training examples, right? So we say we want to print X. This is what we have, right? So it's this and this, right? So no, this is just a mess. And to visualize the data, this is what we have, right? So who can tell me from the top of his head how many clusters we have in this data? how many clusters would you want to define from this data? Now let me make it a more practical example. Now we have a customer base, right? And from this customer base, we have taken two information, their age and their location. And then when we plotted this data, this was 300 mention, right? So mention, we've collected their age and we collected this data of people that we collected, and this is what we have. Anyway. Can you hear me?
We can now.
We can hear now, but your voice was breaking like for like 3 minutes.
Oh, seriously. I'm so sorry. Okay, so as this says, we have 3 clusters, right? So, but funny thing is that if we have 10 different locations in 10 different locations in Munshi, or different sub-local governments in Munshi, and we have ages ranging from say 10, or let's make it 18, ages ranging from 18 years old to say 60 years old. Do you think 3 clusters might really define the, or might really pick good pattern? Do you think 3 clusters means anything? Truth is that if you define 3 clusters, or it will pick 3 clusters that kind of find similarities between, heavy similarities between these different people. If you pick 4 clusters, it will find 4 clusters that kind of defines good similarities between these same people you get. So, like I told you guys before, it's dependent on whoever is doing the research, right? And for this simple case, from the top of our head, we can just say 3 clusters, because you can see that they are widely separated. But of course, this large space here, this large space here, and this large space here. Now, how do we implement it if we are doing it with code? Mind you, there are libraries we can use for this, but with this code, it kind of brings into your mind what we have explained before now, right? So remember all those things I was saying, trying to describe to you guys by having a center and then the movement of the center to find the best center and all that. So that's exactly what we want to do. So the first things first is to define the number of clusters. But the approach we are going to do is we want to just have functions that implement the different activities for the algorithm. So it's quite much, but I'll explain everything, right? So remember we said, okay, I think I will go through this approach. I'm going to go down to here. So this is the algorithm itself, right? So we said we want to define a value k. And K is the number of clusters we want. So we say we want 3 clusters, right? And clusters is invariably going to mean we have 3 different centroids. And remember, we said we want to randomly initialize the value of the centroids, or the value of mu. And yeah, I can hear you.
Sorry, wait, I can't. The screen I'm seeing right now is still like the first cell.
Wow.
So like the network is making the whole process to land.
Is it the same with every other person?
Yeah, it is.
Okay, is it my network? Okay, wow. Okay, let me see.
I can see the visualization.
Okay, still the visualization you're seeing.
Yeah, stuck at the visualization.
Okay, let me stop the sharing and start again. Okay, so what do you see now? What do you see now?
Define function to implement k-means.
Okay, makes sense. So maybe I'll just go back a bit. So I said to implement k-means, we've already defined the functions that kind of implements the algorithm. Yeah. And it won't make any sense if I'm just going through the different functions and how it works. It won't make any sense to anyone. So I think the best approach would be to go to where we are running the algorithm. Yeah. And then use this to understand what these different functions are doing. Yeah. So it's down here. I'll still go through all this. I'll still go through all these other things later as we move on. So it's down here, clusters. And in this case, when we say we want 4 clusters, yeah, well, let's say 3 clusters. And then we want, because we know we want 3 clusters, we want to find randomly initialize the centroids, yeah. So the centroid is the value, is that mu that we saw in the algorithm that I showed you guys earlier. And that is what this function here does. Right? So now this function takes in your input, which is your x, your features, and then the number of clusters you have, right? And if we go up to see the function, which is here, right? It takes in your input and your clusters key, and then it returns random index positions, right? Based on the shape of your x, right? So it's returning 3 random positions based on the shape of your x, right? So this shape of your x is based on the column shapes of your x. So it's going to give you, say, a random value. Let me show you what it looks like here, right? So you're going to be having a value something here and a value something here. That's the first random. And a value something here. Let's say C and B and E and F, right? So this is what it's going to look like. So you know, this will define the first centroid, the position of the first centroid. This will define the position of the second centroid. This will define the position of the third centroid. So it is for the 3 clusters that we have defined. Make sense? I assume it makes sense. And then we set the 3 positions to be the centroid. So now we set these positions that we have defined here to be the centroid x, and we just return x. So if we print, let me see, let me as we're going through it, I'll be printing so that you guys can see. So now let's see what x is. Let's say we pass in 3 and then x, the input here. So let's see what x is. X. So you see it is 3 random initializations of positions. And then if you plot it, right, this is what it looks like. So you see it started out randomly, and these are the 3 positions. It just found 3 random positions. If you try it again, another random initialization, you see this is what it is here, right? So this is just, we've not started learning anything. We've not started finding any centers, right? So these are the 3 random positions. And then let's go back to our algorithm. Where is it? Okay, here. And then next thing we do is to define a distort, which is just a list. So now what this distort is it gives us it's doing. So remember that loss, that plot that we had of the loss. Yeah, this is what this distort is going to do. So we want to be saving the distance at each iteration inside this list here. And then we want to plot this distort on a 2D plane to know how it was reducing through the training process. Then we have a for loop. So now we are saying we want to go for 10 iterations, right? And the first thing we want to do is to get a closer examination of the x, that's the centroid, small x, and the data x. So what we want to do here is that, remember then I told you guys that we would want to find, let's say this is our centroid, right? We want to find the points that are closer to this centroid, the points that are closer to this particular centroid. That's exactly what this function is doing here, right? So if we look at it here, you'll see that, yeah, it looks like one big complex code. It's not. Just take it bit by bit and you'll understand. So we are saying that for I, we define a, this is the C, yeah, our clusters, right? So we are saying for I in range, the shape of X. So we are taking the shape in its column wise, right? Not the number of training examples. We want to find the minimum position of all the data points when you calculate the distance with respect to the centroid itself. So for those of us who did some form of mathematics in everybody did mathematics, well, maybe I think this one is further math. Yeah, I don't know. Well, it kind of finds this formula of x1 minus x2, sorry, this one is x2 oh, x2 squared plus so this, let's say this is so now this is with respect to the centroid. So you won't have this here. You won't have this. So what you instead have here is your, what you instead have here is your mu, is your mu mu1, and you have your x2 minus your mu2 squared. Yeah. So this finds the distance between that x, the position x, and the mu. It's not a straight line. It's not a straight line. If it was a straight line, and this was your x, and this was your mu. This was your mu here. Oh. Yeah. What you just do is the distance. If this is say 3, and then this is say 7. So just the 7 minus 3. That's the distance. But now it's a 2D plane. So this is the formula you use. This formula here. Yeah. And that's exactly what we implemented here. So we are finding the sum of the difference squared of each of the data points. So now we are saying the first value of x minus the first value of the centroid, the second value of x minus the second value of the centroid. Then we are summing it up. Now we are finding the squared, right? And then we are summing it up in the column y-axis. No, sorry, this row, right? So summing everything up and then finding the square roots. So that gives us the distance, right? So now, but you're not going to be having distance for, what you're going to be having is the distance. So let's say it's x for the first string example, right? So let's say this is the first string example, right? So you're going to be having the distance for, let's say this is the first string example 1, right? So you're going to be having the distance with respect to mu1, with respect to mu2, and with respect to mu3. So you want to pick the minimum distance between these three, right? And sorry, that's what would save. So when you pick the minimum distance, that's what you would save in this C here, right? And this C is your different clusters. So invariably, since we have three, what's the name? 3 different clusters that we defined. You're going to be having, I think, 3 different lists in this place here. So let's see what it looks like here. So when we say we want to take a closer examination, let's look at what C is. Okay. So instead of, I think the approach used is that if the first example is this, before I move on, let me explain something which I just figured out. So now this numpy does argmin. It returns the position of the minimum distance, right? So now remember, for our clusters, the first cluster is in position 0, second cluster is in position 1, the third cluster is in position 2. So now the positions, what this argmin is going to return is the positions of the minimum distance with respect to the centers that we have defined. So now, if the minimum distance is 0, it means it is pointing to the first value of x. That's the first value of the centroid of mu that we have. If it is 1, it's pointing to the second mu value we have. If it is 2, it's pointing to the third mu that we have. And that's what we append here. So now, C, as you would see here, is all the data points. But now, it's corresponding to all the data points. So, but each index of C, as you would see here, has like each index of C corresponds to each data point that we have, and the value 0 means it is closer to the first centroid. Value 1 means it's closer to the second centroid, and value 2, as you see here, means it's closer to the third centroid. So let's see the shape of this. Sorry. Oh, there's no shape. There's no shape. It's not numpy. Let's do length of this. So it is 300. So it's for the 300 training examples that we have here, right? So it's for the 300 training examples. Is it clear? Is there any question?
Yes.
No, yeah? Okay, so let's move on. Okay, so we understand what happens here. And the next thing to do is to calculate the distortion. It's just basically trying to save the distance for every of the for every iteration, right? So I'll go back to this discussion later. I won't do it now. Let's just first of all finish the algorithm, then we'll go back to the discussion so that everyone gets to understand the important thing. Discussion is also very important, but I'll go back to it. So now let's say we didn't do this, right? We now moved ahead to move the centroid. So remember I told you guys that after we have calculated the distances, let me go back here. So let's say it was here, 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 and we calculated the distances after random initialization. We need to move the centers that we have defined so that it is at a position that is a mean to every other point. It's at a position such that the position is like the positions of every other data point around it. All right. So if it was here, and then you found out that this guy is close to it, this guy is close to it, this guy is close to it, compared to every other centroid that is here. If you say it is everything here, you should find a mean for all these data points and move your centroid to that position. And that is exactly what this particular part of the algorithm does, right? So the move cent function, and that is what we have here. So what it is basically, like everyone would know, is we are saying 1 all over now we are moving in range 3. In range 3 because we know it is for 3 centroids. We have, meaning that we have 3 clusters, right? So we are saying for the first cluster, we want to find the mean. For the second cluster, we want to find the mean, and for the third cluster, we want to find the mean. Remember we said that the 0, 1, and 2 points to the 3 different clusters we have defined, right? So we are saying, so 1 all over the total number of, so that's why we have the shape here, shape 0. That's yeah, shape 0, column-wise. So we want to say for the total number of x, where x, the value of c is equal to I, right? So we want to say we are doing for the first cluster that we have defined. So where c is equal to I, if it is 0, it means all the values of 0 that are in this list C, like I showed you guys earlier. You want to know how many of the training examples, how many of these points are in that particular cluster, right? And then we want to sum all of those different points, right? We want to sum all of those different points and divide by the total number of points that exist. That gives us the mean, right? So if we find the mean, it gives us the mean of, it gives us the position of mean. So what it is this, we say we are taking everything here. We want to say for everything here, how many are they, right? If we know how many they are, we add up the different values that are here and divide it by the total number of points that are in this cluster. So that's what this is. That gives us the new position of our centroid, right? And this here just plots our centroid. Okay, so let's run it and see what it is first. Then I'll go back to show you what the distortion does. Right? So now let's say no, I want to show, yeah, so this is the plot, right? So this is what it is. Now let's say we define my number of iterations to be 2, right? Let's see what happens. Let's say it just changes the value of the centroids 2 times. Let's see what the plot would be like. So you see that it's still trying to adjust itself, right? So you see this point is at this one, it's at this position here. This one is at this position here. It hasn't really gotten a good let me use the word loss, right? So let's say we increase it to 3. Three kind of does better. So the reason why it's faster is because the data set is quite easy. It's a very easy data set. But for some other complex data set, it might not just be three training examples. So let's say 5 this time around. Yeah. So you see, it's still the same thing. But now what happens when we say we want 4 clusters? Confused. Yeah. I would say the algorithm is confused. So, but let's increase iterations. Let's say 20. So it means that it's calculating more loss. Oops, I hope it's charged. Okay, it's fine. Okay. Sorry, please. Let's put off the stuff. Okay. So you see, it's the distortion is calculating more loss. We'll still go back to this, but let's see whether it works fine. So you see, 4 clusters, as you would see, it's not really doing fine. But let's initialize it randomly again and see what happens. Okay, so I'm looking for what's to cluster. It can't really find anything to cluster. So it's you as the engineer that will say, okay, it's like this cluster isn't doing well. And then you also take into account the loss that you're having. Here we're having 0.68, yeah? And let's see what we have when we say 3 clusters. It's quite higher though. Okay. Let's see. Well, of course, performs far better than the previous one. Okay. Let me go back to what the distortion does. Yeah, what we do in distortion. So this distortion, what distortion is. Like I told you guys, it's basically calculating the distance for all the training examples, taking all the training examples as a whole, right? So, but now instead of you might want to confuse it for this that we have here. No, it's not. Here we are saying we are looking at the shape of the training examples, the number of columns that we have. But for the discussion, we are looking at the number of centers that we have, right? So we are saying that we are trying to know the cumulative distance with respect to the data point with respect to the centers that we have defined. So we are saying where for each of the different centroids, what is the distance of this centroid, of this training example, right? And its centroid, right? What is the distance of this training example, for each of the training examples, rather? For each of the for each of the centroids, what is the difference between the sum of all the training examples and the centroid? So it's still the same formula we use here, right? But we're now saying it is the sum over all the training examples, right? The sum over all the training examples that have been assigned to a particular cluster. I don't know if it makes sense. So it is quite different from what you have here. It's not the same thing as what you have here. Instead of what you have here, instead what you're having here is you're trying to find the distance of each training example. But here you're trying to find the sum of the distance. You're trying to find the sum of the distance of all the training examples assigned to a particular cluster, right? And then you're finding the mean. So we're saying 1 over the total number of training examples in that particular cluster. So we're finding the mean, the total number of distances. And if you pause the distortion, that's what you have here, right? This gives us the test multiplied by some one. This is what you would have, right? It's changed, it's no longer changed. And that's what you would see here. So it reduces, it starts from something around 1.5 and then reduces on, okay, right? That's what gives us. So that's it for running the algorithm. I have about 10 minutes. So that's it about running the algorithm from code. So let me quickly just go through the other bit of it. So like we're going to use the k-means function in SQL. It's a cluster function. I have it's a cluster class of SQL. And when you import it, what you just want to do is this is the serial data set. The one we have here. You just want to pick your value of x, assign it to this time around we call it x1, so there's no conflict with the one we have from code. So let me quickly just go through this on scikit-learn in SQL. It's a cluster function, it's a cluster class of the same shape 300 by 2. And then we call the k-means function in SQL, and we pass in 3. So this 3 just means the number of clusters that we want for our training. And when we pass in 3, you say it and you put it in a very initialize it with km1, and then just like every other SQL, yeah. Sorry. You import it. What you just want to do is the value of x, assign it to this time around, essentially 300 by 2. And then we call the k-means
Your voice is cracking.
and we pass in,
Wow.
and when we pass in 3, it's put it in a very
Yeah, your audio is cracking.
Hello.
Said your audio is cracking.
Hello. Can you guys hear me?
Yeah, we can hear you, but your audio is not that good.
Okay.
Your audio is not that good.
Hello.
You're coming out broken.
Hello.
We can hear you. You're just coming out broken.
Hello. Is it better now?
Yeah, you're fine now.
Okay. Might be, I need to find how to fix. I need to know how to fix Okay. So which parts did you guys did I break out at what point? Is it at this point or where?
At the implementation using SQL.
Oh, okay. So let me go again. So if you're going to use sklearn, right? like I said, you would import the sklearn library, and then there's this k-means function in the sklearn, right? And we are going to be using it on the same data set. So for the same data set, we load the data set. This time around, we want to save it in a new variable, k1, right? And then if you're going to initialize the function, you'd need to pass in the number of clusters you want. And in our case, we want 3 clusters, right? So we pass in 3 clusters and initialize it with km1. And then for every other sklearn, majority of all the other sklearn functions, we all know what .fit means. So .fit means you want to train the model, right? So to train the model, we pass in our input, and our input is x, right? And when we run this, it gives us the results. And you'll notice that sklearn already implements the k-means plus plus method of initializing your values of mu. So we don't need to even go stress ourselves and then try to implement it. When we did this, we were just doing random initialization, but it kind of worked well because of the way this data set is structured. So, but sklearn already implements the k-means plus plus for you. And if you do the km1.cluster_centers, it gives us the different centers, the different optimal centers for the gives us the different optimal centers for the what we are trying to train. So this is our but look at this as the positions of our value of mu. These positions here, here, and here. And then when we plot, this is what we have. And it is very similar to what we have here, right? So you notice these two green points here is the same thing as this. So you can also see that our algorithm, the algorithm we defined here or here, is actually okay. It's still very good, but it might not perform well in initializing the values of the mu when it gets to complex problems, as compared to when you use the k-means plus plus method of initializing the mu, right? But it still did a good job. Something that's par with what sklearn would give you, right? So that's it. That's it for k-means. But that's not totally it for k-means. How many minutes do I have? I have 3 minutes, and I still want to go through PCA. But now this leads us to the assignment I want to give everyone. So this assignment is similar to what we did some time ago, some months ago, where I told you guys to play with the pixel values of some images and tell me what you noticed. Some guys played and then it changed the colors and the pixel values, and then we saw some very interesting things. But now let's see how we can apply k-means to compressed images. So let's say we have an image, right, which is the image of a bird. I didn't plot this image, but it's fine. Don't worry. I think I can still plot it here. Doesn't matter. But this is what the image looks like. It's the image of a bird, right? I think this is a parrot. So it looks like a fish also, but it's a bird. And we want to compress this image to be something like this, right? So now, this is the image. We know the image is a 128 by 128 image with 3 color dimensions, RBG. Yeah. But how do we use k-means to compress it to clusters such that it will just have some uniform color, right? First things first is that you would want to scale down the values of the pixel. And the easiest way of scaling down is just dividing it by the maximum number. The largest value of the pixel is 255, right? So dividing all the pixel values in the image by 255 kind of scales it down. And scaling it down will give us better results. And then we would want to reshape the image. So now we want to reshape it to be a 1,638, 1,000, no, this is not 1,000, 16,384 row value to a column, which is just a RGB. Yeah, so it's by 3, 16,384 by 3 inputs data. Right, so I won't call it image this time around. And what we did here, you can look at it as it's something called flattening. So we are flattening the image out, right? So we are taking the pixel and spreading it out, unfolding it. Yeah. So it is now going to be like a row value, like a row. Everything in this 128 by 128, which you'll visualize as a square, becomes just one row. Yeah. And now, for my own case, I said I want to divide it into 3 clusters, right? And I just pass it through the k-means algorithm, right? So what these 3 clusters is going to do, or what I did, let me just summarize the whole code. When you go, when you guys try it out on your own, I want you guys to think about everything I said and try to see how it makes sense in this code, right? So I'm saying 3 clusters, meaning that I want to find 3 different points in this image. And from these 3 different points, which are the clusters I have defined, or the similarities I have defined, I want to then change the pixel values to be the value of the 3 different mean, the mean of the 3 different clusters I have defined. So when I say I want a k-means of 3, right? When I say I want, oh, why is this doing this? Okay, so when I say I want a k-means of 3, it's going to give me 3 different positions, this, and this, right? Remember, we have flattened this out. And of course, the labels will be 0, 1, and 2, just like the previous example, right? And if we plot that, you're going to see that as compared to this image we have here, it picked similarities and said, from the similarities I'm able to find, this is what it will be in 3 colors. And you can see here, there are just 3 colors in this image. Black, based on the position, remember it is based on the position, right? So it says, I can categorize everything here as something similar to black. Same thing with these guys here, same thing with these guys here, and same thing with these guys here. And then these guys too, I can say it's also similar to black. These guys, they're also similar to black. These guys, they're also similar to black. So let me just cluster them together as black, right? Then these guys here, this guy here looks very bright. I don't know what color it is. And I think these guys too are bright. But compared to this guy, there's a shade of black here. So let me say everything that has a darker shade of say a yellow or red, let me assign it to this color here. And the one that has a lighter shade, let me assign it to this color here. So this is what your new cluster would look like. This is what your clustered image would look like. So, but now what happens when we say we want it to be 3 clusters? It means we are most likely going to have, no, let's say 4 clusters this time around. I hope I have not broken the code. Okay. No, let me make it 10 clusters. So it makes more sense. What are we going to have, right? So it says the 10 clusters means we are going to have 10 different positions, right? And these 10 different positions are going to translate to be this. So it is not the same exact image, but it has been able to find 10 different colors in this image and cluster them, 10 different colors that kind of have high relationship with all the image, the color combinations in this particular image, and it clustered everything together. Or it plotted the image based on the clusters it has defined. Let me change it to, how many minutes do I have left? I'm past my time. Let me just take 5 more minutes. Let me say 6. Okay. So you see, it goes on and on. Sorry. It goes on and on. And we say 100. 100 will be something closer to the image that we have. I hope my system hasn't gone. Okay, it's plotting. So you see 100 is something closer to what we have here, right? So it has found 100 different clusters. So 100 different clusters might invariably even mean the whole image itself. But of course, I don't think it's all the image itself. It's still kind of compressed. So that's it for k-means. So what I want you guys to do is maybe take any picture that you like, a picture of yourself, and see what happens when you compress it using k-means algorithm, right? So now PCA. So I'll just go over PCA. It's a very short thing. So we are also using k-means. We are using scikit-learn, sklearn, right? And for the sklearn, we are using the iris data set. So the iris data is just a data of now this is to answer the question. I don't know who asked, but it was like, is it just for supervised is it just for unsupervised learning? Can't it be used in supervised learning? And I remember I said that you can use it for supervised learning kind of problems, but you are not having anything to do with the ground truth, which is y. So now the iris data has 4 different features. It has the sepal length. Iris data is the iris flower that you all know. It has the sepal length. It has the sepal width. It has the petal length. It has the petal width. And then they all, based on these 3 different features, you can use that data to predict whether it is an iris setuna, iris versicolor, or an iris virginica, right? So these are the different classes. So it's actually a classification problem. Yeah, it's actually a classification problem that you would probably use a supervised algorithm, supervised learning algorithm to solve. But now we want to use principal component analysis to kind of visualize this data. And this is in 4 dimensions. The features is in 4 dimensions, right? It won't be easy for you to plot out this image, this particular feature in 4 dimensions. So we can use principal component analysis to reduce it to a 2-dimensional shape. So now if we check the shape, we have 1,000 training, we have 150 training examples and 4 different features. That's our X. Remember, we are not considering the class, which is Y, right? And now we say we want it to be, we want to reduce it to 2 dimension. Yeah. So all we just need to do is, remember, we have imported PCA here. We imported PCA here. So we just say pass in the number of components that we want, right? And the number of components we want is 2. And with this, we've initialized the PCA. And then we do .fit. So we just pass in this X data into the .fit function, and it transforms it for us. So we pass it in, it fits it, but for us to transform it, we need to do a PCA.transform, right? To get the X in its reduced form. And then when we plot it, right, we find out that instead of having a 150 by 4, we are having a 150 by 2, right? And this is what it is here, a 150 by 2 image. And from the top of your head, or from the top of my head this time around, remember that we already said it has 3 classes: the iris senota, iris versicolor, and iris virginica. This I think corresponds to the iris setuna, right? So, but these 3 different colors correspond to the 3 different classes. So you can just see from a 2D plot that, oh, after I use PCA to reduce this, I can actually even visualize it and see that, oh, this one corresponds to this particular class on this plot. This one corresponds to this particular class on this plot. And this one corresponds to this particular class on this plot, right? So you can still reduce it further to a 1-dimensional, to 1 component, meaning just 1D, right? But the question is that, would it make sense if you do that? Would you be able to visualize anything reasonable if you do that, right? And I think that's it. That's it. Is there any question, guys? Okay, so we have 12 people. Any question, guys? It's the end.
Okay, I have a question.
You okay?
For the iris data that we just use PCA on, based
Yeah.
on based on our reduced dimensions, can we use that as an alternative to classify it instead of using already?
So you could use it as an alternative to classify it, right? You could use it, but I don't know whether I would really advise that in some cases. I'm not. You would want to use it in a situation where probably the model you're using is not able to, on its own, find good patterns, and that's kind of the problem that neural networks try to solve. Neural networks take it bit by bit. It kind of finds patterns on its own. For example, if you're using a convolutional neural network, for instance, convolutional neural networks or convolutional layers are good at finding patterns on its own. But let's say you have a data and then you don't have the alternative of probably using maybe a neural net or some feature finding algorithms in your classification. You can say you want to use a PCA, but one thing you should also understand is that your principal component analysis might throw away some information that you might need. Remember, it's kind of approximates or brings different features together based on what it understands. So invariably, it's a dicey thing. You might be losing data and you might be gaining data. So what you can do is just visualize it in 2D and then still try it out. Try out classification using your normal algorithm without PCA. Then you can also try out classification after you have reduced the dimension, right? But if you're going to do classification after you have reduced the dimension, you have to also compare whether it performs better when you use PCA on it, or whether it performed better without PCA, and then you consider the one that performs best, right?
Thank you.
Yeah. Any other question?
Sorry, my question is not.
I can't really hear you.
My question is not pertaining to this class. Are you hearing me now?
It's still quite low.
Okay.
Okay,
Can you hear me now?
Yes, better now.
All right. So my question is not pertaining to this class. I have an pertaining to this project.
Okay.
So I think I read my email, so I could just access the form.
Okay.
Presently, I am not in the project. So what can I do, or how?
Okay. Even though I didn't hear you clearly, I think I can guess what you're saying. You sent me a message on Slack. I replied. So I said the form is still open. You can just fill it. I actually thought I would see your so just fill it. The form is open. I reopened it.
Okay. Then I'll do that.
Okay.
All right. Very much.
Yeah. Okay, any question? Customer segmentation, guys. Any question? Sorry, customer segmentation guys and ladies. Any question? Okay, since there's no question, we can call it a day, yeah? Because the deep learning class has to start now. But if you have, so now for the practice question I gave you guys, please, once you're done, put it on the Slack group. Let it be motivation for every other person to do theirs, right? Please. It's a very simple thing. The solution is there. You don't need to go stressing yourself. Just implement it, and then the link to the repo is the codes are already on the repository. I think I pushed it. So but I'll confirm that, push it, and then send the link to the group, right? So I think we can call it a day. Thank you very much, guys.
Thank you.
Yeah.